Hi, my name is Neha Sarandasu, and today I will be discussing how varying different components in formulation affect the performance of liquid soap. Since 2018, the industrial value of soap has risen to about $186 billion in the United States, especially after the COVID-19 pandemic. It serves as a basic cleaning agent and has also made a huge profit in other industries such as personal care and cosmetics. It's used in a variety of different cleansers and moisturizers, body washes, and other beauty products. Currently, many consumers are drawn to this more organic or natural ingredients in their products. Soap consists of three main ingredients, which I will discuss further later: oil, lye, and water. And because these three ingredients are so accessible, it is very easy and safe to make at home. Soap is made through a chemical process known as saponification, where triglycerides found in common oils, such as vegetable oil, end up reacting with a lye solution. The two main types of lye are potassium hydroxide and sodium hydroxide. To make liquid soap, KOH is used, and for hard soap, NaOH is used. If we look at the saponification reaction, we can see that triglyceride is derived from an oil, typically a vegetable or plant oil, that contains three fatty acid chains attached to a glycerol molecule. After it affects with the lye solution, the lye dissolved in water, the hydroxide ions break the bond between the triglyceride and glycerol, which ends up producing fatty acid salt, otherwise known as soap. So to prepare each soap sample in the lab, we first heated up our oil, which contains our triglycerides. Then we added our dissolved lye. And lastly, we ended up stirring the mixture until it was fully homogeneous. For each sample, we performed a shake test to measure foamability and a penny drop test to measure surface tension. So the most important part in soap making is knowing how much lye to use. Too much lye can be really harsh on the skin and cause irritation. So for a full saponification reaction to occur, the number of moles of lye must be equal to the number of moles of fatty acid chains in the oil. So in order to determine that precise amount of lye required, we need to use the oil's saponification value. As you can see on the chart, each oil has a different SAP value depending on whether KOH or NaOH is being used. So for this experiment, we investigated the effect of varying oil type, oil concentration, and water type. First, we examined the effect of different oils on foamability and surface tension. As we can see from our results, we found that coconut oil had the highest foamability compared to olive and castor oil. This is because coconut oil contains mostly shorter saturated fatty acid chains, which are known to have higher solubility and better lathering properties. Olive and castor oil, on the other hand, contain more unsaturated fatty acid chains that are longer and a lot less soluble. So with surface tension, it was expected that coconut oil would have the lowest surface tension due to its high foamability. When there's more foaming, the distance between the intermolecular forces increases and the attraction becomes weaker between the molecules, which ends up reducing the overall surface tension. However, we can see that coconut oil ended up having the highest surface tension, which may have been due to inconsistencies in the penny drop test method. Next, we varied the concentration of coconut oil while keeping KOH constant. We used a baseline of 60 weight percent coconut oil, which contained the required amount of KOH needed. As expected, we can see that the baseline produced the highest foamability because a full saponification reaction was able to occur. Lower concentrations, however, produced too much lye and created an almost like watery consistency. Similarly, with higher concentrations, they had much lower foaming heights than the baseline because there was way too much unsaponified oils or excess oils that caused the soap to separate quickly and become rancid. And then for surface tension, it was expected that the baseline would have the lowest surface tension because it had the highest foamability. But even though it's lower, we see that there is no significant difference between surface tensions at 60%, 65.2%, and 69.3%. And again, this may be due to those same inconsistencies with the penny drop test. Lastly, we observed the effects of different types of water. As expected, distilled water ended up producing the highest foamability because it is clean and harsh minerals. Hard water contains excess calcium and magnesium, which reduces the bubble formation. In lab, we ended up using a calcium chloride additive to replicate that hard water. On the other hand, salt water had a slightly higher foamability than hard water because salt has a lower ionic strength than calcium chloride. And ionic strength is important to consider here because it increases the pressure on the bubbles being formed and can cause them to break and reduce the overall foamability. And as with tap water, it had the lowest foamability because of its high mineral content. Lastly, if we look at the surface tension, we can see it follows the expected trend, where those with higher foam heights produce lower surface tensions. In conclusion, it was determined that coconut oil had the highest foamability, yet lowest surface tension, which again may be due to those inconsistencies with the penny drop test method. This was also seen with the surface tension when we were varying the oil concentration. However, we did find that the baseline concentration produced the highest foamability. And lastly, for varying water type, we determined that using distilled water gave us the highest foamability, and surface tension followed its expected trend where higher foamability reduces surface tension. Thank you for your attention, and I will now be open to any questions.